All right, discrete mathematics, folks. First section, section 1.1, introduces something called propositional logic. So I've got a definition written up here. A proposition is a declarative statement that is true or false. It's a truth value. Before we get into talking about examples, I want to motivate the study of this subject for those who are interested in computers. Computers are made of circuits. And a circuit kind of involves two things. It has digital signals that are bouncing around within it. And digital signals are made up of this idea I mentioned in the previous video of either on or off, right? A digital signal is on or off. We represent the on and the off numerically with 1 or 0. Another way to think about this is true or false. The signal is on, true, or the signal is off, false. And then circuits are not just signals moving around. They're signals moving around and interacting with one another in what are called logic gates. And logic gates generally use things like operations like and, or, not, as well as other operations. There's NAND and NOR and XOR and a bunch of other operations we're going to learn about. These are the most common three operations, sort of the basic ones. So computers are doing logic all the time. And if we want that logic to mean anything, then what we need to learn how to do is interpret the world logically and represent it symbolically. So in this chapter, chapter 1, we're going to do a lot of that. We're going to spend a lot of time translating between verbal statements, and representing those verbal statements symbolically, and then manipulating symbolic statements using rules of logic. So our fundamental type of object we're going to work with in this chapter, in this logic, is a proposition. It's a declarative statement that's either true or false. Let's look at a few examples. Example A. The moon is made of cheese. All right, well, that's declarative. It's declaring something. And it's either true or false. Happens to be false, but that makes it still a valid proposition. Here's another one. 2 plus 5 equals 7. That's a valid proposition. It's declaring something, and it's true. So let's look at a couple of non-examples. So sometimes in order to understand an idea, it's useful not only to look at what it is, but also to look at what it isn't. So how about sit down? It's not a declaration, right? This is more of a command, right? It's not something that you could say is true or false. So this statement has no truth value. It's not a proposition. That's not the type of statement we're talking about working with. Here's another one. 2 plus x equals 7. Okay, close. It's a lot like 2 plus 5 equals 7. This is more of a question, though, than a statement. It's not like quite a declaration. This is something, 2 plus x equals 7 is something we will be able to work with, but we need to develop a different idea called quantifying. When you have a statement involving a variable, your variable needs to be quantified in some way in order to turn it into a valid proposition. I'll explain what that means in a later section. So the problem with this statement here is that it's not quantified, and that would make it not a valid proposition. So there we go. So we have these ideas of propositions, and these are like the fundamental things that computers work with, basically statements that represent true or false. The value of one of these things is true or false, but it might be tied to some real-world idea by a statement like this. Now, a lot of times we're going to use variables to represent propositions. So common propositional variables are, as you can probably imagine, the letter P. It's a popular one because it stands for proposition. And so if we're going to use P, we might as well use Q and R and sometimes S as well. So those are pretty common letters we use for propositional variables. So in algebra class, you're used to working with X and Y, or maybe A, B, and C. We could use those letters if we want to. But in logic textbooks, you'll often see the letters P, Q, and R used to represent the propositional variables. Think of them like X, Y, and Z, or A, B, and C. They're just variables whose value is either true or false, 1 or 0. And they may be representing or, kind of like equal to some verbal statement. Now, I do want to mention something before I end this video, and that is that what I'm teaching in this class is only one particular type of logic. It's called classical logic. So in classical logic, a proposition is either true or false, and there's no in-between. That's something called the law of the excluded middle. There's no such thing as neither true nor false, and there's no such thing as true and false at the same time. There are alternative logic systems that incorporate those ideas, and they reject the law of the excluded middle, but we're not going to learn those. If you're interested, you can Google something called intuitionism, and that is one of the more popular non-classical logic systems. However, computers are based on classical logic, and so that's what we'll be learning in this class.